Okay, welcome back. This is the second part of the video on surface integrals, and we're deriving the formula to evaluate a surface integral of a scalar function. The main idea, remember, was to pull the problem back via this parameterization. So where we left off was we were looking at approximating the area of the surface patch S sub ij by the area of the parallelogram determined by these vectors that we called P sub 0, P1, and P2, and they were the images under the parameterization of these 3 points, these corners of this rectangle in the UV plane. All right, and what we saw was in our previous video that we can approximate the vector that connects the point P sub 0 to P1 by this partial derivative vector, times delta U, and we could approximate the vector connecting points P0 to P2, which is the lower left and the upper left corner there. We can approximate that by this partial derivative vector with respect to V times delta V. Alright, so we're kind of doing a double approximation here. Alright, but as delta U and delta V shrink to 0, these approximations will improve the error and the approximations will go to 0 also. Alright, so now what we're going to do is write down that approximation to the surface area of the surface patch, the curved surface patch S sub ij. We said it's approximately equal to the area of the parallelogram determined by the vectors connecting P0 to P1 and P0 to P2. Alright, and we know from our work earlier in this semester that that's going to be equal to the area, or sorry, the length of the cross product vector. Alright, now what we've just shown is that we can approximate these vectors. Alright, the first one connecting P0 to P1 by the partial derivative of r with respect to u, that's a vector, times the scalar delta u crossed with the vector, and we are approximating P sub 0 to P2 with the partial derivative of v, or of r with respect to v, times the scalar delta v. Alright, now really what we have is parentheses around these two vectors that we're taking the cross product of. What we're going to do next is just pull these scalars out. We're assuming delta v and delta u are both positive numbers, or positive constants. We can take these outside of the cross product length, and this will then be the length of the cross product of the partial derivative of r with respect to u and the partial derivative of r with respect to v. Again, we're at the point u sub I, v sub j. I'm leaving that off for now. And then it's going to be times on the outside of that, delta u times delta v. Again, we're assuming delta u and delta v are non-negative numbers. Those are positive constants. We can pull them outside of the length. Alright, so what we're going to say then is when we look at and I really shouldn't have surface area, but delta S sub j, that's when we look at delta S sub j in the Riemann sum, that means the surface area of that. We're going to then replace that, because that's approximately equal to exactly what we have here. Okay. So it's the length of that cross product vector times delta u times delta v. Alright, so let's continue on then. Alright, so now so that was the long part of it, is getting that, approximating that surface area of that piece of, or that patch of surface on the surface we're trying to integrate over. Again, we're talking about the surface area of a scalar function, so we're restricting the scalar function to the surface, and we want to integrate over the surface. Alright, going back to the limit definition for the surface integral. Alright, so we're going to now use that right now. What I'm doing here is, instead of writing a single sum, alright, and letting k run from 1 to n, alright, we're going to think about this as a double sum. Okay, and the reason we're doing that is we're counting up the total number of subrectangles we have in the UV plane by using the partition for the u-axis and the v-axis. And notice this number capital N here will be the product of whatever M and P are. So the number of partition points on the u-axis and the v-axis, we're going to have M times P rectangles in the UV plane. Alright, it's just a total number, but it's more indicative of the integral we're going to end up with if we think about that as a double sum by letting I sum up and letting j sum up. That'll give us the total number of subrectangles and therefore the total number of surface patches. All right, now let's focus our attention on the expression inside of this Riemann sum. We can think about that, again, pulling that back via the parameterization. The special point that we're going to pick, which is the ordered pair, or the ordered triple, I should say, x sub k star, y sub k star, and z sub k star, we want to pick the lower left corner, and that lower left corner is the image under the parameterization of the ordered pair u sub I, v sub j. So that's what we're replacing x, y, and z by. And then we're replacing the size of the kth piece of surface area, or surface patch, by delta s sub I j. Alright, so let's change the notation slightly. We're using the parameterization r now, and then we're going to approximate this by the function value at r of u sub I, comma, v sub j, times, now what did we say before? We had that the length, or the surface area, we could replace in terms of the length of the cross product times delta u delta v. So let's put that in there. So it's times the magnitude of the partial derivative vector. Again, this is at u sub I and v sub j across the partial derivative vector with respect to v of the same point. And then that's going to be times delta u and delta v. All right, now what are we going to do? We're going to add those up and then take the limit as delta u and delta v approach 0. Okay, so just putting that into the Riemann sum, what would we have? We would have the double sum, all right, on I and j, and then we would have, just rewriting this expression down here, just for convenience sake, I'm not going to put the dependence on, we're evaluating both of these partial derivative vectors. It's the length of the cross product vector of those partial derivatives evaluated at u sub I, v sub j, and then it'll be times delta u and delta v. What is this going to turn into, right, as we let delta u and delta v shrink to 0? What's this whole thing going to turn into? This whole expression is going to turn into, well, the double sum is going to turn into the double integral, and we're going to replace delta u and delta v. That's going to be du dv, or dA, and then we're going to have f of r of u v times the length of the cross product vector, length of the partial derivatives, length of the cross product of the partial derivative vectors, and then that will be with respect to area. All right, so dA here. All right, we're thinking about dA is replacing delta u times delta v. All right, and that's the result. All right, and then we got the formula in the box that I'm going to show now. So if we have a piecewise smooth surface and we have a continuous function f, we can integrate the scalar function over the surface, and this is how we do it. All right, so we have to use a parameterization of the surface. So we're assuming r is the domain of the parameterization. Capital R is the domain of the parameterization in the UV plane. Little r is the parameterization function, and that's how we evaluate a surface integral. Okay, a couple of comments to add on to that. All right, so again, we're pulling the problem back via the parameterization little r to a region in the UV plane. Typically, that's going to be a rectangle. A couple of the bullets below, we call a surface smooth if it can be parameterized by a differentiable vector valued function such that each of the cross product of the partial derivatives, and we'll write it using the del notation and also using the subscript notation, which we have here underlined here in yellow, as long as the length of that, or as long as that cross product vector is not the 0 vector, so it doesn't have magnitude 0, then we call the surface smooth. All right, again, that kind of eliminates the possibility of corners or cusps in the surface. One other thing to note as well is that a surface integral does not depend on the parameterization. All right, so if we change the parameterization, as long as it describes the same surface, then for a general scalar function, the surface integral will not depend on the parameterization. In the next video, we're going to talk about surface integrals of vector valued functions and show how those can be viewed as a special case of surface integrals of scalar functions where we have to carefully choose the parameterization. All right, very similar to what we saw in the first video earlier on line integrals and viewing those line integrals of vector fields as a special case of line integrals of scalar functions. All right, last comment here is that surface integrals are tough to compute. All right, so the surface integral of a scalar function can be difficult to compute because if you look at your formula, if we look at the formula, then we have to compute quite a bit to write that expression down that I just underlined in pink. We have to compute both partial derivatives vectors. We then have to take their cross product, and then after that we have to take the length of that cross product and then multiply that by what we get by plugging in the parameterization into the function. That's a fair amount of work. These problems can be long and tedious. All right, so this is a complicated expression that we have here on the right side. All right, that'll be it for this video. In the next video, we will discuss surface integrals of vector fields or vector functions.